Okay, so it's a great pleasure to introduce Thomas. Despite what you might hear, the British and the Germans are great friends. And Thomas has been coming here for 10, 11 years. It must be at least 10 or 11 years. Been a great supporter of the course. And he's going to give his presentation on the current state of hearing preservation, which I'm sure you all find fascinating. Thomas.
Okay, thanks a lot. Thank you much, John, for the introduction. Recently, the Queen was visiting Germany, and she was very open speaking about the European Union and that the British should not leave it. So we hope that they will stay in. We need you. I mean, and vice versa. So.
Well, remember, she does have a certain German connection going back in history.
Yeah, we always had it, and I think it was quite good until 100 years ago. That was a bad time, but I think it has improved quite a lot. And you can be proud to have a queen. I mean, she would be perfect to represent as head of European Union. I mean, I think she is head of 16 nations on the 16 countries. And she would be perhaps perfect in doing that. But that's something about politics, and as John, you said, perhaps we have to stay innovative in the future to really serve our patients best, and perhaps we have to do some inventions and innovations which are not basically on the high tech, and you said about what you have to do in South Africa, and now I speak about some high tech. So just the contrast. But I'm not sure how long we can really pursue it. So let's see what we have today, and it's perhaps still something out of the golden ages of medicine. Okay, well, hearing these orders, actually we can very simply just speak about the outer ear, the middle ear, inner ear, and the auditory pathway. And I think we can be quite lucky in some parts of the world that we have nearly for all types of hearing loss something available for treatment. And that's besides the middle ear surgery. We have seen a perfect demonstration this morning. It is on hearing devices, and this has grown quite tremendously. It's not only on the hearing aids, but also on the implantable devices, where we are bridging parts of the middle ear and transferring sound directly into the inner ear by mechanical stimulation, but also where we are replacing the inner ear, the inner hair cell, by electrical stimulation or even beyond. And then we have combinations which are coming up, so to serve patients with partial deafness and other related components of hearing loss. Now, auditory implants basically can cover different degrees of hearing loss, starting from here very low up to profound. And we also can use them for mixed hearing loss, where we have, in addition to the sensory neural component, also a conductive component. And you see here just from one company how they basically would divide up the whole empire of hearing loss. So to say, for any of them, there are solutions out. Okay, now let's go through that. And the first thing is bone conduction. It has been out in the field for a long time. It's the BAHA, the bone-anchored hearing aid, with a percutaneous screw. Recently, also transcutaneous solutions have been found for patients with either pure conductive or loss or single-sided deafness. And the first one is the bone bridge, which basically has an active component compared to the BAHA, where you just have only the screw in the skull. Here you have an active component with a receiver, and you need a transducer placed on the skin. So it drives the internal part, and this part is basically shaking. So it's fixed to the bone with screws. That's the important thing, that you really have a stable connection. And then with that you can get a good improvement here. Just a comparison between this bone bridge and the old BAHA system in terms of gain. You see here kind of the unaided threshold air conduction, and then that's what you get with the aided, so it's very comparable. So the transcutaneous system works. It might be a cosmetic aspect. but in terms of indication, in terms of effectivity, it's basically the same as the percutaneous bar. Now, differences are seen in surgery. When we just go back, you see it's quite thick piece. It's about 7 millimeters, and you need to drill quite a lot, expose dura if necessary, and also in children there are given limitations by age. Okay, then there might be other limitations such as magnetic resonance imaging. That's more difficult to do with that device in the head than with just a simple bar screw. Okay, that's now look on active middle ear implants. I mean, they are really out for patients who have more pronounced hearing loss. So the sensory neural component is more than 30 dB, and the Baha concept doesn't work because it does not provide enough amplification. So now let's look on just what these implantable hearing aids are doing. That's the acoustic hearing aid, the conventional one, which stimulates in the outer ear canal, and the sound has to drive the whole middle ear and the inner ear, and we get kind of distortion, higher amplifications. We have the problem of also driving quite a large volume, and then we get unfavorable transfer, especially on high frequencies. And this, of course, then limits the benefit of this acoustic hearing aids. The electric stimulation is in the cochlea, that's a cochlear implant, and then just in between, somewhere from the ossicular chain to the inner ear, we have this implantable hearing aids, mechanical implantable aids, which stimulate mechanically some of these elements. Now, the most widely used is the vibrant sound bridge. You see here, it's attached with a clip to the incus. That was the original setup for patients with pure sensory neural hearing loss who were not able to wear hearing aids due to chronic external otitis. And you see it's clipped here. It's a permanent magnet outside a coil, and then by the electric field, which is an AC field, then the magnet is driven forth and back between these bumpers, and this then creates the movement, as you can see, as mimic. Okay, here, so that's a floating mast inducer. It's also a two-component system, one audio processor, receiver, cable to that. You see here intraocular view, how it's fixed, so it should freely move. And then you can serve patients that have this amount of hearing loss, should not exceed 40 decibels, 45 decibels at around 500 hertz, and then you still get enough gain, as you can see here, across frequencies, more here, and then the patient will have quite a lot of benefit. 65 dB presentation level, you see, it comes up from 20 up to something like 70% in our series of patients, but it's the same also what's published. Now then, of course, you could use this very nice small electromagnetic transducer and couple it to any other location in the middle ear. So a lot of ideas came up, and a lot of inventions were made. Couple it with a torque, with a porp. You also could couple it on a piston, but also on the round window. And this all had been tried, and it works quite well. But there are given limitations, just because this small transducer cannot produce more than a certain amount of vibratory energy. Coupling strategies, just to line out. One is on the round window. You see here the so-called floating mass transducer might be too large to be coupled directly to the round window membrane. Then you can use this kind of rounded coupler, which allows you to do it very effectively. At the back side, you have some cartilage so that it's safely placed. The other is here on the oval window. You also could use this kind of a compound construction. It's very similar to what Robert likes. I mean, you see, it's also not that easy sometimes to create it, but in principle it works, and it's quite efficient if you have good coupling it. And so we have direct to round window coupler, oval window coupler. Okay. Now, when we need more power, then you basically need two points of fixation. So that is then given with the Otology's middle ear transducer and the totally implantable version called Carina. The principle is a transducer, which is basically fixed here at the rim of mastoid, and the tip, which is moving, is connected to the incus body. That is the initial installation. And you see they can serve patients that have more pronounced inner ear hearing loss, or sensory component is larger, so it's up to severe hearing loss. That's possible. The fully implantable version has also an implantable microphone and an implantable battery package. So you basically wouldn't see an outside transducer, but of course you have some issues with feedback or body noise the patient hears about with the microphone. So this might be then a problem afterwards. Here you see also other coupling modes, for instance on the staples head here, as you can see it here, or you also can couple to the round window, the same as we have seen it before. And then there's an even more powerful device, which is basically going directly into the inner ear. So why should you do all this, coupling and all this kind of difficult constructions if you would directly go into the inner ear? Something that also Robert prefers in many patients where he does a stapes prosthesis, and this is connecting directly into the perilymph. And that's taken with this device. It's direct acoustic cochlear implant. So you see the name cochlear implant, but it's not an electric cochlear implant, but it's acoustic. And what you see here is, again, fixation system, transducer. Here is a kind of artificial incus, and this system then couples into the inner ear with a piston. So you can open the inner ear through the footplate, for instance in advanced otosclerosis or tympanosclerosis, but even in patients with mobile footplate, it's doable. And then you just couple the vibratory energy directly into the inner ear. And that is very, you see here again, it's, and that's very powerful. You see here the construction works easy to do the clipping. It's not that easy to go through the posterior terminal. It really takes some experience to do that. Indications, as we see here, the profound mixed hearing loss. And here you see how it's done through the posterior terminal. You actually can expose the round window and then place the staples through the perforation. You also can do it a combined approach with additional transmeatal procedure, but normally it's not necessary. Now what do we get? Well, that's the unaided threshold. AC, that is bone conduction. Basically no change in bone conduction through the surgery, so it seems to be quite safe. And that's what we get in terms of gain, that is unaided, that's what the hearing aid gives, and that's what the patient gets with the DACS device. So as you see, it's very even across frequencies, from low to high, and it's better than with the hearing aid. And that's what you also see in these results. So here's monosyllabic word test, an SRT, and you see the blue bars with hearing aid, the green bars with this device, and you see some of these patients, they actually had no speech understanding with hearing aid pre-operatively, but then they jump up from 0 to something like 90%. It's unbelievable, but it shows the impact that it has to go directly into the inner ear. And here, highly significant improvement as it's shown here. And that's another way to display it, pre-op, word recognition score, post-op, and to see if patient is in this part of the graph, then there's improvement. So that's quite remarkable. The same is true for 80 dB presentation level. Okay. Well, now patients who basically don't have enough inner ear reserve, and there are not many hair cells left, but the auditory nerve is still functioning, they are then the candidates for a cochlear implant. And the cochlear implant replaces the inner hair cells, so the transduction of sound into auditory nerve action potentials. This is then just taken by the implant. It's very rough, it's very crude compared to the inner ear. We have thousands of hair cells, but here you have perhaps only 20 or 16 or 12 contacts. But it seems to be enough in order to provide different sensations between high and low pitched sounds. And that's all you need for speech understanding. It's not enough for music. For music you need more, but for speech that is enough. And so it's just an example. So that electrode stimulates, and then these adjacent nerve fibers are activated. Okay, now indications. Well, bilateral profound to severe deafness, adults, children. Other indications are the high frequency deafness, we'll show, and the single-sided deafness. So in the meantime, the implants are so good that patients even with single-sided deafness can use the hearing with the implant and combine it with the hearing from the other side and get the benefits of binaural hearing. Okay, the main prerequisite for cochlear implant is first you need a cochlea, and second you need a nerve, and that's you can display then in magnetic resonance imaging. In terms of electrodes, a lot has been done to make them better in terms of placement, in terms of trauma. The main thing would be to move them as close as possible to the nerve. So lateral wall going medial, that has been achieved by some preformed electrodes. You can see here nicely in the temporal bone specimen that this can be achieved in some of these cases. In terms of speech processing, as I said, we have only a limited number of bands, frequency bands, and that's what is then assigned. So you see each of these frequency bands is then assigned to one of these electrodes, and then the patient gets this different pitch, which helps him to understand speech. Surgery has been standardized, not in the Netherlands. They use you see very funny surgical strategy for cochlear implants. You would not believe, but here you see it's very straightforward. Posterior incision, pouch mastectomy. You go then through posterior terminotomy to the middle ear. You find the inner ear through the round window, and then you can insert your electrode very slowly. I think there are a few issues with electrode insertion, independent from the electrode. Slow advancement, avoid rapid shock-like movements. We want not to traumatize the ear anymore. Cochleostomy wide enough to avoid pressure increase in the cochlea, and don't go over point of resistance. So that's basically what you should follow. So once the electrode is in, we want to make sure that everything works, and then you just stimulate the nerve, and then you can record responses from the nerve. You see here, so for instance, this electrode stimulates, then the adjacent nerve will respond, action potential is produced, and then you can record with the device itself with other adjacent electrodes, and this signal then is basically then displayed and can be seen on the screen of the measurement system, and you know the nerve is responding, and for children you also get some values for postoperative fitting. Okay, well that's just, second is we would also like to see that the electrode is placed correctly. So we take any kind of X-ray, intraoperatively preferred, and you see it's right in place. So you can find some surprises. I mean, if you don't do it, it might be that it's somewhere, especially in malformations. I think it would be very good to have it at hand. Okay. Now, what has been achieved? Well, 1978. You see very close connection between therapist and patient, and you see that's a small speech processor at that time. That is the microphone, just let's begin. And they had some awareness of sound. 1990, speech recognition in a few. 2015, most patients have speech recognition, and in the future we want to achieve it for all of them. Well, the main thing that has been improved is speech processing. Just the amount of information that is transferred, and you see it's just by the microelectronics. So the microprocessor that is in the implant and outside in the speech processor has become more powerful. That means they can provide now several thousand pulses per second, and that, as you see, is paralleled with an increase in the performance, so just correct speech understanding. Okay, well, the second thing that has really brought it forward is bilateral implantation. 2 years are better than 1, and that's true for cochlear implant recipients too. So sound localization, improved hearing and noise, that's basically what you get with 2 years. Now, one development that has become more and more important is to serve patients with residual hearing, because there might be some speech understanding, but still not enough. And even with hearing aids, the patient might not be able, for instance, to use a telephone. And that's something which is very important in nowadays society. So it would be desirable also to serve patients, for instance, like this audiogram shows with high frequency deafness. Hearing aid, any kind, also implantable, would not work because there's nothing to amplify. And the only thing you can do is restore hearing here with electrical stimulation and combine it with acoustic hearing in the low frequencies. So, for instance, this part of the cochlea is, so to say, implanted, and then you would present these frequencies electrically, while these lower frequencies are presented acoustically, and that's called a hybrid system. You see a hearing aid component, cochlear implant component. Okay, so special electrodes have been designed, atraumatic, and they are inserted in a special way. I hope that I can get this running. Okay, here we have it, yes. So you see it's through the round window, and you make a small slit, and then you can insert these electrodes very slowly and get them into place, and that's the same is true for here in this case. Electrode is a bit longer, and then it's inserted very slowly. Okay, good. So it's possible to preserve residual hearing. You can see here actually pre-operative, post-operative, very little change. Most of the patients really keep their hearing also on a longer range, and they get better speech understanding and noise. That's what you have. Signal to noise ratio is something like, let's say, +6, +7, and then it goes up to 0, which is a huge improvement. And you see it's mainly beneficial when you listen to speech and noise, but also some acoustic hearing that is preserved gives you some music hearing, which is normally with cochlear implant alone not possible or very restricted. Neural deafness, so we are at the end of the journey. Patients who don't have an acoustic nerve anymore, doesn't work due to tumor, due to trauma, whatever, they basically would not benefit from stimulation here, but from stimulation beyond the nerve. And that's the principle of the Otolaryngology brainstem implant. So you just stimulate here in the second neuron, and you also could go even higher up, go up to the midbrain and stimulate in the same way. So this is also possible, but one must say the results are much poorer than what you get with cochlear implant. And it's actually something which fortunately is needed only in very few patients. So it's less than 1% of people who are deaf have a neural deafness. 99% have sensory deafness, and therefore these devices are really restricted to those who might need it. Children with agenesis of the auditory nerve, of course, also can be served. Okay, so summing up, so we can basically serve all degrees of hearing loss with any kind of these devices, and I think the journey will go on. We will see future developments, and we hope that the accessibility for those solutions out in the world will improve. But I think that's something which is a big challenge, not only in South Africa. We see it in many countries that probably there are no funds for those who would need it. And especially the situation for children is desperate, because you can't do it later. You must do it in a certain time in their life. And unfortunately, even so, we have these wonderful devices that's not available for many of them. It might change in some of the countries like China, like India. They have a kind of upcoming economy, but it's for sure that it's not out there for many who would need it. But it's a situation where we only can hope that it will kind of improve. Thank you for your attention.
Thomas, for a fantastic presentation from the House of Hanover, which as ever appears to have incredibly good support on technology. Very interesting to hear. I'm sure there'll be some questions. We've got a few minutes before we have a break, and then after that we'll go into the final operation with Renaud Pirou. So questions from the audience. Professor da Costa from Brazil.
Hello. Good.
Good to see you. Are you all right, Saint?
I'm all right.
Thomas, what's the behavior of the residual hearing in this electroacoustic stimulation? You have the follow-up of how many years to see if it remains stable. And if not, if you lose it, is there any problem to reinsert a new electrode that will cover all the cochlea?
Yeah. There is an initial risk to lose hearing, which is with this kind of special electrodes less than 10%. No? Over time, over several years, you have some patients who lose hearing. Yeah? As you said, then the question is what to do. You just see whether these shorter electrodes gives enough hearing. If not, you can go and exchange it to a longer one. And there are currently concepts being developed that you basically insert only part of a longer electrode, yeah, in order not to risk residual hearing, because longer electrodes have a higher risk for initial hearing loss, so that you can then, if needed, insert it deeper in. This would be perhaps a solution. But you are right, there is a risk for delayed hearing loss.
So, but is there any risk of the implant itself to generate an inflammatory process and then later on ossification of the residual cochlea on the apical turn, so you cannot reach this position of the cochlea with a longer implant later on?
The experience is not that. The experience is that you can easily insert longer electrode. What might happen is that you get some reaction to the implant, and probably there is also kind of electrode toxicity. So the stimulation, electrical stimulation itself, might be deleterious to hair cells, not to the neurons, but to the hair cells. And it's not quite clear whether we have a charge density limit that should not be exceeded. So, I mean, if you, let's say, stimulate too high, so too much current, then probably there is a risk for that. Which is, I think, something to be considered, and especially if you look for future therapies. I mean, one would be a bit cautious with that.
You do it through the window when you do electroacoustic?
Yeah, we do it through the window. Yeah.
What about if it's not electroacoustic? You also go for the window or go cochleostomy?
In most of our cases, we do it through the window, but some of these electrodes, not for hearing preservation. Do you see these thicker electrodes? Probably it's difficult to get them through the round window. So you can enlarge the round window just anteriorly, inferiorly, and still stay in the scalar tympani. For us, the reason to use round window approach is because you are in the right scala. And to place your cochleostomy, if you don't use round window, you can be surprised when you look on post-op location of electrode that perhaps you have a lot of placements not in the scalar tympani, because it's sometimes very difficult to check except precisely the place where it should go.
Thomas, sorry, just one more question. I don't know if you have experience with this. In South Africa, we sometimes have a meningitic child that hasn't got funding or anything, and so we go in and we place a 1/0 suture, just in the curve to try and keep it open, hopefully that it won't ossify. We've gone back on a few occasions and it's actually been open.
It's very good, yeah.
But I've only done 3. But I mean,
it's just the, how you call the placeholder or something?
Yeah, what's not sizer?
That's just
depth gauge.
Depth gauge or whatever. Yeah. Just to keep it open. Yeah.
Just to keep it open.
Yeah. I mean, it's a good thing. We would use some, as you say, the depth gauge or probe electrodes or whatever.
Okay.
But I mean, that's much cheaper.
Yeah, that's what.
And you can put it out easily. It won't grow in. Yeah. No, it's good.
Okay, Manohar Bans, Halifax, Canada.
Sorry, Thomas. I enjoyed your lecture. Thank you. Thomas, do you have any experience with the ABIs in children with agenesis of the cochlear nerve, and what have your results been if you have any experience with that?
Okay, yeah. So we have a series of children with this cochlear nerve aplasia. Also, some patients where we had cochlear aplasia, but there was some sac left and placed a cochlear implant, but they did not respond. So, I mean, there are several conditions, but in principle, it works. The point is that it should be done not that late, so we would go for implantation in the second year of life, and then you can expect, when you look on this categories of auditory performance. So there's just a grading between 1 and 10. 10 would be open set speech understanding. You could use telephone and so on. And normally they come up to 5, which means that they have kind of not only sound identification, but also they have a closed set speech understanding to a certain extent, and it's a support for lip reading. That's clearly to say. We have also some who are better. They have really open set speech understanding, but we also have several who are poor. So I think it's a very wide range, and on the other hand, there is no alternative if you would like to give some auditory sensation. I think it's due to the etiology, because there might be also damage higher up in the auditory pathway, and you can't check it preoperatively. There is so far no diagnostic method. I mean, with MRI and fiber tracking, it's still not there. It's too small. I mean, the small size of the child, it really limits it.
Can I ask you a quick other question? When you there's electrotoxicity that Bruce Gantz keeps talking about, residual hearing. When you activate your implants for the electroacoustic hearing, do you cover them with steroids during the activation process like he does?
Well, something what he says, we start low and then we increase. What we have seen is that in some patients, not immediately, but after a certain 1 year, 2 years or so, they come up and say, well, hearing has deteriorated. And then you check the impedances, electrode impedance, and then they are high. So it seems to be that something has occurred, and then with higher impedance, you need higher voltage to drive the current through, which means higher charge density. So I think it would be good if you would have a kind of a telemetric measurement of the impedances. So the impedances are measured automatically, and it's kind of checked by the system. And if you see they go up, then probably there's a warning, stop using the device or something like that. Because it's not only immediately at the time of first fit.
Okay, any more? Okay, well, thank you very much, Thomas.
Thank you.
Fantastic. Well, like a little bit of housekeeping for those watching on the live stream, we're going to have a 15 to 20 minute break to recuperate. Then we're going to come back and watch Renaud Pialou, and then I think as a special added attraction, we're going to slow grill a Frenchman. We're going to put Robert out at the front and ask him a little bit more about Malleus relocation, and perhaps Wilco will join in with that. Okay, thank you.